Okay, our last lecture. Again, just want to remind you that throughout the year, if you're ever interested in reviewing any of these, you can go to our department website. Before we get, I have this also at the end, but before we get too far into the material, I wanted to show you what we've changed this year from previous years. In previous years, we've handed out a paper form for you all to fill out and give your feedback so we know how to improve the course. If you go to Events and Lectures, we're the second link here, Introduction to Biostatistics. If you've been here and you haven't registered, I encourage you to register because that's how we're trying to build up our email list for events like this and to send you information about this particular class. The lectures, the link to each of the lectures is here, and now we have a course evaluation. So we're going to try to capture some demographics like who's utilizing the course, MD, PhD, what your degrees are, what your position or your appointment, your gender, your race and ethnicity. Tell us which of the sessions you attended in person and if you've viewed any of the recordings as well. That way we can kind of figure out what your overall exposure was to the course whenever we're looking at your feedback. We want you to basically rate the usefulness, the organization, the pace, the level at which the stuff is taught. So if it's too low or if I went too slow and covered, for instance, the sampling distribution too long, then let me know that. Here you can indicate which areas you think need more time devoted or less time devoted. You can select as many as you want. I believe if you click Other, it will pop open a box and give you some other options if you wanted to provide text feedback. Instructor, and then what aspect of the course was least and most effective, and then your overall impression, and then, of course, a text box here for any feedback that you may have. And we do read this, believe it or not. It's not just captured and stored in a database somewhere. So I try to take it into account. And the more and more this class is taught, the less and less it changes because I tend to get the same types of feedback, so it's just being refined. But there may be something next year that I've never covered that you all would like to see. Please let me know, because I know there are some things that I would like to cover personally, but because of time constraints, I've not been able to capture in this set of lectures. Things like Poisson regression, which is very useful for data that is counting events. For instance, like the number or frequency of rehospitalizations or frequency of infections. That is a continuous outcome, but it's really a count, and we treat count differently than we treat something like blood pressure. So it would have its own set of methods that really are not, they're not beyond the scope of this course, we just haven't had the time to cover them. So when I get your feedback, for instance, about things that we could spend less time on, then maybe I'll think about pulling some of that stuff out and adding in new methods. So let's continue with hypothesis testing. You'll recall last week we covered two things. We covered more than two things, but we covered two particular methods. Both of them were dealing with comparing a continuous outcome between groups. So the examples that we had, if you'll recall, were the traumatic brain injury. We had that score that measured cognitive function or cognitive status, and it was a continuous score with an average of 0, and it varied from approximately -3 to +3, but it really was continuous. We assumed that within the population it behaved like a normal distribution, and then we showed how to do, for instance, a one-sample test to see whether or not our population really had a mean of 0, and then we did a two-sample test comparing two different groups in terms of their means using the two-sample T. We did not cover dependent samples, but I indicated what the difference between independent and dependent samples were. We also talked about what would we do if we didn't meet the assumptions of the t-test and how to check those assumptions. So again, remember that for any method that I cover, there should be some non-parametric alternative that doesn't have the restrictions like normally distributed, or a sample size of 10, for instance. I'm just throwing 10 out there as an example. That's not necessarily a cutoff point for anything. For instance, the equivalent of a 2-sample T could be the Wilcoxon signed rank test. That's probably a common one. We also covered when we have more than 2 groups that we're interested in comparing. Either we have 3 populations or 3 different treatments, 2 treatments and a control. How do we do that? The answer is not to do a bunch of 2-sample t-tests doing a bunch of pairwise comparisons, but to do it all in one structure, which we call analysis of variance, or ANOVA. That controls the chances of us making an error through essentially what some people call data fishing. It's sort of the same process. The more tests you do, the greater the chances of you making a discovery that isn't actually there. So that's why we choose to use ANOVA rather than a t-test when we have more than 2 groups where we're comparing means. Again, ANOVA has the same assumptions: continuous outcome compared between groups, normally distributed outcome, approximately equal variances. Now, it's easy to understand how we check for normality. Just do a box plot. Not a box. Well, you could do box plots. You could do box plots, but you could do histograms. How to check for equal variances? The easiest way to do it is to create your summary statistics, get your mean for each of your groups, get your standard deviation and your variance for each of your groups. And if you see a variance that's more than 2 times bigger than the smallest, then you know you violated the assumption of equal variances. There are also formal hypothesis tests that we could do to test for equal variances, but we won't cover that in this course. And again, the limitation of the overall ANOVA is that it tells us if there's a difference, but it doesn't tell us where the difference is. So that's when we do post hoc procedures, where some adjustment, it essentially is like doing a bunch of 2-sample t-tests if you're doing pairwise comparisons, but you're making some adjustment to when you would flag something significant. So I'm sure most of you have heard of Bonferroni's adjustment. That's one way of doing it. There are actually a large number of ways that you could make adjustments to control the error rates. The one that we covered last week was called Fisher's LSD. It's actually the most liberal, meaning it's most likely to find significant differences, most likely to find differences. So 2 ends of the spectrum, Bonferroni, which you're probably familiar with, which is essentially just dividing your error rate among all of the tests, versus Fisher's approach, which really does no adjustment at all. It's like doing t-tests. So it really depends on what is important for your design. Today, we're going to continue looking at comparisons between groups. Essentially, that'll be like the theme here. But we're going to change the type of outcome we're looking at. So last time we had a score that was continuous over the range -3 to 3 approximately. Today we're going to look at responses that are like success, failure. So if I'm interested in seeing whether or not the rate of success or the rate of failure is different between groups, I would not use a t-test. The primary purpose, or the primary reason I wouldn't use a t-test, is because the t-test makes the assumption that the observation is continuous, that it comes from a population where it is approximately normally distributed, and we cannot have normally distributed categorical outcomes. So new methods are required. Chi-square is one of those methods. I'll also give you some non-parametric equivalents when we get through there. A different type of outcome, which we briefly touched on earlier in the course, is a time-to-event outcome. How do we compare time to event between groups? The set of methods or the types of analyses that are applicable to this kind of question are called survival analyses. Some events that are interesting would be like death or infection or rehospitalization, anything that's an event where you're interested in not only whether or not the event occurred, but the timing of its occurrence. That would be a survival analysis, and we'll cover that today. What if we have a continuous outcome, but rather than comparing it between groups, we're interested in whether or not it's associated with another continuous outcome being measured on the same subjects. In that case, we would be doing something like correlation, statistical correlation, not the English term correlation. And then what if we wanted to adjust any comparison between groups for some other additional factors that are maybe prognostic for the outcome? Then we would want to apply what are called regression methods, which give us some flexibility and allow us to build more complex but maybe more meaningful models of our outcome. Please feel free to stop me at any time. Right now I'm going to start with chi-square, and we'll end up with regression methods. Time permitting, I'm going to try to cover some diagnostic test stuff. If we don't have enough time to cover that, then what I can do is, if you're interested, you can always send me an email, and I can send those slides to you separately, because they're pretty standalone. They don't really build on anything beyond themselves. Any questions? Okay, so what if we have a response, a patient response, that looks more like success-failure than a score like we had last time? What do we do? Well, in this case, we're really still interested in a mean response, but that mean is not an average of a continuous outcome. It's an average of a binary outcome, a category. So what you end up with is a percent or a proportion that describes the average behavior of subjects in different groups. I'm going to give you an example with genetics, just to kind of, obviously a made-up example of genetics, but this can be applicable to clinical application as well. For anything, just imagine that you have some kind of binary characteristic or outcome for your subject. So in this case, we have one characteristic that we're interested in, and it's a genotype that has two different levels: double A, double capital A, or capital A, small a. So we'll, for the sake of me not having to say double capital A, I'm going to call this major and this minor. So of the specific genotype of interest, we are looking at whether we have major or minor for each of our subjects. So the dependent variable y in this case is actually the proportion of samples out of the 100 tissues that you have that demonstrate each of the genotypes. You may think that in the population that you're drawing from, the breakdown of major and minor is about 75-25. So 25% of the population would express minor, 75 major. This is what you hypothesize, by the way. We don't know what the population looks like. This is sort of, if you recall last time, the sampling distribution. It's not as easy to see here, but when we hypothesize what the population looks like, it starts that process where at the top we have a distribution. We pull from that distribution a sample, and then the sampling distribution mechanism kicks into place, and then we, at the end, ask ourselves whether or not the sample that we observed looks like it came from the population that we hypothesized. So the geneticist hypothesizes that the population of interest has a 3-to-1 ratio, major to minor. So what that hypothesis actually looks like is a null where the population contains 75% major versus an alternative hypothesis, which is actually what we're interested in. Usually, in this case, it's the null. The null is actually what we're specifying. The alternative is the population does not contain 75% of the major. Written out statistically, it's just an equal sign. So this pi, if you'll recall last week, for the mean, we had mu. Pi is a very common Greek letter to represent a proportion. You can think of it as the letter P. So pi 0.75 versus not 0.75. This particular type of test, where you really have one group, right? We have one population. And from that population, we've pulled 100 tissue samples. And we're hypothesizing about the distribution of some factor, some categorical factor, in that single population. This is what's called a chi-square goodness of fit test. And I'm giving it this name because there are other types of chi-square tests. They are all going to essentially do the same thing. But if you ever see chi-square goodness of fit versus chi-square test of independence, for instance, you'll understand the difference. So what we have here are differences between what is expected and what is actually observed. Remember last time when we talked about what a test statistic does. I demonstrated how we could interpret the T. And if you'll remember, the T test statistic was what? It was a number that was really in units of standard deviations, and its magnitude represented how many standard deviations are observed between what we hypothesized and what we actually saw in the data. The chi-square statistic, this nice Greek letter here that looks like an X, is doing the same thing. If you just look at the top of this, it's the observed frequency minus the expected frequency squared, and it's summing it over all the categories of X. So the categories that we're interested in here are the two different genotypes, the major and the minor. So what I observe in my data minus what I expect divided by what I expect. And then there's a formula to show you the computation here, but I just wanted to highlight here that this statistic, which is a test statistic, is doing the exact same thing as the t-test. It will grow in size as the difference between the hypothesis and the data increases. So big values of chi-square indicate stronger evidence against the null hypothesis. When you have a chi-square, just like with the t, and I didn't really emphasize this last time, you have something called degrees of freedom. And all the degrees of freedom do is adjust that sampling distribution for essentially, in this case, the number of categories of X. So the degrees of freedom for the test that we're going to look at are going to be 1, because K, the number of categories of X, are just 2, major and minor. And here are just some pictures of what this chi-square distribution looks like for different numbers of categories of our variable X. Suppose the researcher collected the 100 tissues and observed in that sample this breakdown. 84%, 84 of them expressed major, 16% expressed minor. So the question is, this is what the observed distribution of the genotypes looked like. Is it close enough to the hypothesized distribution, which was 75-25, for us to say that that hypothesis really can't be rejected, that the data and the hypothesis agree to some extent? Or is it different enough that we could be confident that we should reject that hypothesis and state that the breakdown within this population of major and minor is actually different from 75-25? We would do the chi-square test. Now, you wouldn't actually by hand compute this, but I wanted to show you at least once what the calculation looks like for a chi-square test statistic. So what is observed and what is expected? What we observed, this is the first category, which is capital AA. This is the second category, which is capital A lowercase a. And you just plug in the values. What we actually observed, 84 of the 100 samples actually expressed major. What we expected under the null hypothesis, remember 75-25 was 75. And then we divide that by 75. after we square it. And then we add it onto the deviation between observed and expected for the second category, which was 16 under the data, 25 under the hypothesis. When we calculate that out, we get a chi-square value of 4.32. And it turns out that is large enough. If we went to a distribution in the back of a book, or you could actually, there's lots of programs online where you can compute the p-value for a given statistic. This lowercase, this little 1 down here, by the way, indicates the degrees of freedom of the test. So for this particular set of observations, it turns out that we would reject the null hypothesis that the breakdown is 75-25. So it appears that the geneticist hypothesis is not correct, and this should say is not correct. I apologize for the typo, because our p-value is 0.038. It appears that there's actually a higher percentage of major and a lower percentage of minor in the population. So for this example, again, I wanted to reemphasize, when you're doing inferences on proportions, it's because you have a response or an outcome that is categorical. Regardless of the number of groups that you're looking at or the number of categories in that factor X, you can use a chi-square test in the same way. So essentially what you're doing is looking at whether or not there's an association between categorical outcomes. There are assumptions associated with the chi-square test. ROT stands for rule of thumb. The rule of thumb is that no expected frequency. If you recall, there was an E here. No expected frequency should be less than 5. So if you have an event, for instance, that you're interested in looking at the rate of its occurrence, which would be yes, it occurred, no, it didn't, which results in a proportion, and that event is what we call rare, so let's say it's less than 5%, then it's possible you could get an E in that formula that would be very small, smaller than 5. And in that case, you would not want to use the chi-square test. If you have an example like we have, where K is equal to 2, the number of categories in X is equal to 2, you could substitute what's called the binomial test. If you have more than 2 categories in X, so for instance, let's suppose this genotype was not just capital A, lowercase a. Let's suppose it was this one, and a third. In that case, you would use what's called the multinomial test. And I will not cover those. But those do not have the same sample size restrictions that the chi-square test has. They are alternatives, though. So let's suppose, I'm going to give you an example here where, in the previous example, let's differentiate, just make sure we're clear. In the last example, we had one population. We weren't comparing groups. We were looking at the breakdown or the distribution of a categorical factor in a population. Now what we're going to do is we're actually going to either compare a nominal factor between 2 groups, or we could have, instead of just one factor of interest, maybe we have 2 factors of interest, and we want to see whether or not they're associated. So some really good clinical examples could be gender and response to treatment. So for instance, a question that revolves around this could be, if I have a treatment that's interesting, maybe it's for diabetes or something else, do males and females respond in the same way to the treatment? In other words, is the response rate independent of gender? That would be a test where we would be making inferences on proportions, and it would be a chi-square test, assuming we met the sample size restrictions. Another example could be menopausal status and disease stage at diagnosis. So a question like this could be, for the patients that I'm seeing, are menopausal status and disease stage at diagnosis independent, or is there some association there? Meaning, if they're premenopausal, are they more likely to come to my clinic with a different stage of disease than those that are postmenopause. Tumor response and treatment. This is a really simple example because there's an obvious independent variable, which is treatment, and an obvious dependent variable, which is response. So treatment could be A versus B, and tumor response could be they responded or they didn't, or it could be more ordinal, for instance. And then presence or absence of disease, and then some exposure. So there's lots of different examples of when you may have nominal or categorical data on more than one factor, and you want to know, are they associated? So the opposite of being associated means you are independent. So these types of tests are called chi-square tests of independence. And that's to distinguish them from the previous example where we had a single population and we're looking at the breakdown of a category within that population. So again, what are the assumptions? No expected frequency should be less than 5. So whenever you create your contingency table, you should have cell counts that are large enough that you don't have any issues. What does this look like? This is actually the sample size times the hypothesized proportion. Unfortunately, I won't go into that too much. Just know that you have to have sample sizes that are adequate for the chi-square test. If you're using a statistical software like SPSS to do analysis, it will flag when you violated this and tell you the chi-square test results may not be valid because you have one of your cells with an expected frequency of less than something, for instance. If you don't happen to meet the sample size restrictions, then this is where you would use something called a Fisher's exact test. How many of you have heard of this type of test? Yeah, it's actually pretty common. Most people, now that we have computational power, now that our computers actually are pretty sophisticated, some people always do the Fisher's exact test, especially when they have a 2x2 table because it will run fast. And then you don't have to worry about the sample size restriction. So here's an example of when we would have two different factors, for instance, that are both categories, and we want to know whether or not they're associated. So we have here gender, male and female. That's a categorical type of outcome, or a categorical characteristic. And then hair color, which is also categorical. We have 300 subjects, 200 female, 100 male, and all we're doing is observing these two characteristics. This is an observational type of an experiment. We classify them according to each of the two categorical factors into either male or female. There's 100 males, 200 females. And then whether they have black, brown, blonde, or red hair. So you can see the marginal totals. This is what we call the row total, and these are the column totals. When you see contingency table data, your mind should automatically go to the chi-square test or the Fisher's exact test if your sample size is small. What else do I want to say here? So when you see contingency table data, very often you'll see it demonstrated this way. This is the overall sample size. And then within each of the cells of the table, we have a frequency of subjects who are both, for instance, male with black hair, and then a percent. Now, what is that percent? The percent here is the percent that's meaningful, because what we're really interested in is whether or not the distribution of hair color is the same for males and females. So the 32% is the percentage of males who have black hair in the sample. It's really easy to see for the males because the total sample size was 100. So we have 9%, 16%, 43, and 32. Same thing for females. 55 out of 200 is 27.5%. So you see the percentage breakdown. And it would be really meaningful for us to observe whether or not there are any major trends or differences in the way the percentages lay out within males and females. In a table, it's kind of hard to see right off the bat unless there's a huge difference. So what I see is 32, 40, and then I decrease blonde, and red is the smallest percentage. With females, 27, 32, 32, and 8. So this is similar. These are maybe similar, but look at this. There's a twofold increase in the rate or the percentage of blondes for females relative to males. So that may tell me here that the distribution of hair color could be significantly different, we don't know until we test, between the two genders. In the data set, if you're doing this analysis, this is not what your data set looks like. This is how you summarize it and present it. In the data set, you actually have a column variable for gender, a column variable for hair color, and then each row represents a single subject. So subject 1 was male with black hair. Subject 2 was female with red hair. Subject 3, female with blonde hair. When you do an analysis like this, you can't expect to put data in like this necessarily unless you're doing something like creating a figure in Excel. SPSS would require data like this, or at least a summary count over here. So in this example, the researchers hypothesizing that the hair color is associated with gender or not independent of. So the null hypothesis, again, remember from when we started talking about hypothesis testing, the null is always a statement of independence or no association or no difference. So the null is that the hair color distribution is independent of gender. And the alternative is that there is an association between hair and gender, hair color and gender. Again, this is a chi-square statistic that looks at deviations between what we observed in the data minus what we would expect in the data if hair color and gender were really independent. The degrees of freedom for this test look a little bit different simply because now we don't have just a single factor with K categories. We have two factors. Factor 1 is the row variable. Factor 2 is the column variable. So this would be like gender. There's two genders minus 1, so this would be 1. And then the column would be hair color. There's 4 hair colors, right? 1, 2, 3, 4, yeah. So 4 minus 1 would be 3. So the degrees of freedom for this kind of a test would be 3 times 1, which would be 3. So the question that we're asking, does it appear that this type of sample could have come from a population where the different hair colors are occurring with the same frequency within each gender, or does it appear that the distribution of hair color is different between men and women? I'm going to say different because I see this large discrepancy here where there's like a twofold difference in the percentages. If we were to compute the chi-square test statistic by taking the observed minus expected, and since this is a large enough example, I'm not going to go through this, but I can tell you that the expected, again, those E's, are simply calculated assuming gender and hair color are not associated. If you're interested in seeing how this is computed, I can give you a resource or a reference. But in general, most people just utilize a software package to compute the statistic. Notice that the chi-square test statistic is large. I have a subscript 3 to denote the degrees of freedom. So in this case, the p-value for this particular value of the test statistic with 3 degrees of freedom is 0.029. So it's less than 0.05, if that's our cutoff. For p-values that are that small, we reject the null, that gender and hair color are independent, and we assume that there is some association, not a cause and effect relationship, but some association between gender and hair color. Would anyone like to hypothesize about why gender and hair color would be associated? Why would we see a difference in hair color breakdown for males and females? Yeah. Right? I would be willing to guess that more women dye their hair than men, and that maybe they're dyeing it from one of these other colors to blonde. So that could be an artificial type of result because maybe blonde is not their natural hair color. Does that make sense? Now, I told you that it was kind of difficult to look at a table, a contingency table, and see the difference right away. What we could have done is shown to the reader of our manuscript something more visual. And what we see here is a set of two bar charts where we have a distribution of hair color for female and a distribution of hair color for male. Here's the legend, but I've also made them the same color as the color of the hair, so it's a little bit more obvious. Bless you. It's also important to note that along the y-axis, we have the percentage of females, or the percentage of males who fell into the categories. The reason we don't have the raw frequency is because, if you'll remember, we had 2 times as many females in our sample as males. So what would have happened? The female bars all would have artificially looked larger than the male bars, and it would have been difficult to look at sort of a standardized relationship between gender and hair color. So by presenting percentages in these types of charts, when you have varying sample sizes, you actually get a better picture of what the relationship is here. And so I can see right away there are more brown-headed men in my sample, significantly more than in the female sample, and the females have a higher percentage of blonde than the males. So it looks like, assuming that in reality there really is no association between natural hair color and gender, we probably have some brown-headed females who are highlighting their hair, dyeing their hair blonde, which is pulling this down and pushing this up, because red looks about the same and black looks about the same. So when you have contingency table data, this is a really good way to demonstrate it, using what are called stacked bar charts, and this is just created in Excel, by the way. Very, very easily done. This is a special case. Notice I could have collapsed that analysis into 2 categories, blonde hair versus others. When I have a 2x2 contingency table, I have a special case where I'm testing a hypothesis concerning 2 population proportions. So my null hypothesis actually in this case is that the proportion of blonde females is equal to the proportion of blonde males. That's only true when we have a 2x2 table. And the reason that is true is because if I know that I've only got 2 categories and 16% fell in one category, then I automatically know the other. So there's no need to look at the entire breakdown. But that's not the case when you have many more categories in your other variable. But again, you could demonstrate that visually as well, and here you see blonde versus other. And again, with percentages on the y-axis. Fisher's exact test can be used in place of the chi-square test when you have contingency table data. The binomial test can be used when you have the example like we had at the very beginning, where you have a single population and you're interested in the breakdown of a categorical factor in that population, or a multinomial test if you have many categories in that factor. Any questions about inferences on proportions? I will get to logistic regression, which is another way that you can make inferences on proportions, shortly. Let's move on to survival analysis then. So survival analysis is where things can get a little bit tricky. It turns out that a time-to-event outcome really contains 2 pieces of data, 2 different types of data, or 2 different types of information in it. It has a categorical outcome, which is the occurrence of an event. Did it occur, yes or no? It also has a continuous aspect to an outcome, which is the timing of the event. So if you're interested in not only the occurrence of some event of interest, but when it's occurring, then you would want to do something called survival analysis. Now, survival, the term survival makes it sound like this is only for healthcare applications, but it can be applied to anything. It can be applied to quality control. For instance, failure of a production part. How long before it fails when they do all of the engineering and testing. You could look at something within healthcare or within biomedical research aside from death as a survival endpoint. So that could be the time to development of a disease. So did the disease ever develop? Yes or no? And if so, when? And that's the continuous part. The response to treatment. Did they respond to treatment? Yes or no? And if so, when was the response? Did their disease relapse? Yes or no? How long did it take for them to relapse? Of course, death is the obvious. Another example would be something like rehospitalization. So how long after you intervened was someone rehospitalized for the condition? Were they rehospitalized at all? Survival analysis methods allow you to take that data structure and do something with it. Before we get into what the different functions and methods look like, let's define some things. So that the time to event revolves around something we call survival time, or time to rehospitalization, time to relapse, time to death. So time to whatever your event. Very often it's called survival time. The definition of this is the time from a well-defined point in time, which is your origin, to the occurrence of a given event. It's very, very important when you're doing survival analysis that each subject has a well-defined origin, a time zero, and a well-defined endpoint. So it's either the end of the study or the time that they were lost to follow-up or the time that they actually had the event. So survival data will have quite a few different things. One of the most interesting aspects of survival data is this idea called censoring. Censoring is very common in research that we do because in clinical studies, when you're actually doing a clinical study, the length of the study is fixed. Right? I only got funding for 5 years, so I have to recruit for 3 and allow time on the end. But unfortunately, when my study starts, I don't have 50 patients lined up ready to go on day 1. They're coming in groups, right? Or they're coming one at a time over the course of time. So that causes some issues with survival data. For instance, someone who is waiting at your clinic door the day you start your study will come in and have the ability to be followed for the full length of time. But if someone comes closer to the end of your recruitment or your enrollment period, it's possible that something could happen. You could lose funding, you could stop the study for other reasons, and you don't get a full observation period out of them. So the timing at which they come into your study could have an impact on whether or not you observe the event. Some other issues that could crop up, loss to follow-up. So patients' survival times are measured from study entry, whenever you, for instance, enroll them or randomize them, until the date of last contact, if it's prior to the end of the study. If you lost contact with them before you observed an event, then they're called loss to follow-up, and they would be censored in your data set. Other patients that would be censored are patients that never had the event before study termination. So if you were going to follow subjects for 12 months after treatment and see whether or not they relapsed, and a subject was treated, followed for 12 months and never relapsed, then they would have a time in the data set. It would be 12 months, the length of the study observation period, but they would be censored because you didn't observe the event. Very, very few analyses have I ever done where we have what's called complete data, which means that there are no censored times. Very often you have censoring. And the most common form of censoring is right censoring, which is this picture here. So these are the most 4 common scenarios for a patient. Let's look at patient A. Patient A entered the study on their time 0. We followed them until the end of the study, and they never had the event. So we censor them here. Their survival time is from time 0 to the end of study. Let's say it's 12 months. If we had followed them out beyond the end of the study, maybe we would have seen in maybe 2 months that they actually had the event. But because the study ended, they appear as if they didn't have the event, and they're censored at 12 months. Subject B also entered the study. This is their time 0. Now, artificially, they look like they started at the same time, but they didn't. Patient B started at their time 0, and we followed them out to a certain period, and they had the event within the study period. So they have a time, and they have an event, yes. Patient C started the study, and then at some point they quit answering their phone, or they quit coming in for follow-up, and we never really figured out what happened, but this was our date of last contact. And at last contact, we knew that they were, for instance, still disease-free or still alive. So then we record the date of last contact, and we give them a censor. We censor them. And then patient D, another example, keeps going on. Maybe they never have the event. Maybe their disease never, maybe they never relapse. But we wouldn't know that beyond this point. So survival data tends to look like this. You have a column for time. So patient A was 12 months because they were censored at the end of study. Then you have patient B, whose time is 11.6 months. Were they censored? No, they were not, because they had the event within the study period. C, 9.2 months. Were they censored? Yes, because they were lost to follow-up. And D would also be censored at 12 months because they didn't have the event within the period of study. So censored very often is a 0-1 variable in an analysis. And you just have to tell the software that which one of those means they had the event versus they didn't have the event, or they're censored at that time point. But everyone has a time. It may be that the time of the event, the time that they completed the study without an event, or the time they were lost to follow-up. So let's define T as the length of time until a subject experiences the event or is censored. The survival function, which is what most people are interested in, is simply the probability that an individual survives longer than some time T. You very often see that visually through a Kaplan-Meier curve. Has everyone heard of the term a Kaplan-Meier curve? Kaplan-Meier curves, along the x-axis you have time. Along the y-axis you essentially have the percentage of subjects still surviving at that time. So if you have no one censored, meaning you observed an event for every subject in the study, then by the end of the graph, your Kaplan-Meier curve should have dropped to 0, because at that time point, at the end of the study, everyone's had an event. So the percentage surviving, or the percentage without an event at that time, should be 0. But very often, they end up not dropping down to 0. And the reason they don't drop all the way down to 0 is because we have censoring. So anytime you see a drop, at time 0, 100% of the patients, I'm going to use death as the event for this example. 100% of the patients are surviving at baseline. So the curve starts at 1. We get out here to about 3 months, and we see a drop in the curve. What does the drop indicate? The drop indicates that events or deaths occurred at 3 months. How many occurred? If you look at how much it dropped, that will tell you the proportion of subjects in that group who had the event at that time point. So let's assume in this sample here that we have 100 subjects. If this drops down, it looks like 1, 2, 3, 4. Looks like drop down 2%. Then 2 of the 100 subjects had an event at 3 months. Then we go for a period of time with no events, and then we observe another set of events. In fact, it looks like this drop is about the same as that drop. So the events occurred at about the same rate at those 2 time periods. When you start to observe longer drops in the curve, what's happening? More subjects are having the event, right? More deaths at that time point. Oh, look at that huge drop. We had a lot of people have the event here. Then we go for a period of time without the event, and then a lot of events again. And then it starts to taper off, but it's occurring more frequently in terms of the time. So the way that we interpret these curves really is how rapidly they're dropping. The faster that they are approaching 0, the faster death is occurring in that group, the rate at which it's occurring. And you can think about, if you're interested in a particular period of time, look at how fast the curve is dropping during that time period. So if I'm interested in 0 to 48 months, you can think of the slope, the average slope of this line, as sort of the rate of death over that period, right? It's decreasing. If the slope is very, very strongly negative, then you know you have a rather rapid rate of events. Think about if I had a survival curve that came out like this and just barely tapered off. That would indicate to me that patients are not only surviving longer, but the rate of events is much, much slower because the slope of that line over the period is almost 0, very flat. So when we're comparing 2 groups based on their survival functions, functions that are further out to the right, that don't slope off quite as quickly, indicate the event is not occurring as rapidly or as frequently in that group. So in this case, a benefit or better survival would be observed in this group because, if you'll notice, it's primarily because of this lag at the beginning. The slope of the line is about the same through here, but it's delayed before anybody has an event. Here they have events at 3 months. This is at a year before anyone even has an event. Censored observations are generally marked on these curves. I don't see markings on this particular example, but I do have an example where they mark a censored time point just to indicate that it was there. Right, so this is what I would say a short-term benefit. Long-term, it really depends on what you. If you look out here, I do see some difference as well. The median survival is about. There's not much difference in the median survival, right? But if you survive out to approximately 30 to 36 months, then your chances of surviving long-term on this drug are much higher. On this drug, by 48 months, everyone's either censored or dead. Does that make sense? Yeah, these are sometimes very difficult to think. But if you think about them in terms of the slope of a line, everyone knows what a line looks like, right? And how to interpret the slope. Just draw, especially when you have curves like this that are pretty much parallel and straight, just draw a line and think about the slope of the line as the rate of events occurring over that period of time. Sort of an average rate. When you don't have those nice sort of straight curves, it becomes a little bit more complicated because what it tells you is the the rate of events is changing over time. So something a little bit more sophisticated than just the usual methods should probably be used to find those differences and to describe the differences. Here's an example of a tumor DNA profile. The event is death, and the time is time to death or on study in weeks. And we're looking at it for two different types of tumor. Here, it's essentially the same kind of situation before. We see that long tail for one curve and sort of a truncated for the other. So in weeks, by about 250 weeks, this group is done, meaning they've all either had the event or they've been censored. The censored observations on this particular graph are indicated by a plus. So there was an event here that was censored. We probably either lost them to follow-up or some other reason. It should be described in the manuscript. Here, here, and here. What probably happened here, maybe end of study, and they hadn't had the event, I'm guessing. Rapid rate, you see quite a few censored observations in this one. And the proportion of censoring should be wherever the curve stops. So if there were no censored observations, this should drop to 0. This one looks like there were a little bit more than 20% of censored observations in the blue. Does everyone see that? And about 10% in the orange. So which of these has better survival? Yeah, the blue, right? Better survival in the blue. Why? Because on average, it's above the orange. So at any point in time, the probability of survival is higher in blue than it is in orange. So you're really looking at vertical distances here for probability of survival at any particular time point. And in terms of time saved or time gained, you kind of look at the horizontal differences here. So your question is, you think that whenever you look at the curves, visually you see a difference, but when you do a test, your p-value does not indicate that it's significant. Survival data is very interesting because it's not only the length of follow-up that's important, and it's not only the sample size that it's important, it's the event rate. So if you, for instance, if you're comparing two groups where the event is not occurring very frequently, that is really your sample size. How many are having the event? If you have 1,000 subjects and 2 have the event, you're not going to be able to see anything because the real sample size is the 2. So in your example, is the event occurring, how many events do you have in how many subjects? Do you remember? Uh-huh. Yeah, you can definitely make best guesses or estimate what your sample size would need to be for a given period of follow-up and an average rate of events. So if I know that in 3 months, if you have 100 subjects and you expect 30 of them to have the event in 3 months, then I could give you a power sort of calculation. If you think that in 6 months, an additional 30 would have the event, then I could tell you, I could give you an idea of whether you could do what you want to do in 3 months or if you should go out to 6 months or if you need to increase your sample size. So there's a lot of considerations beyond, you know, it would take more than just a quick discussion between you and a statistician. But if you had the data and the information, a statistician has tools that in simple cases, really, you can plug some numbers in and it can tell you and give you a good estimate of your sample size required for a period of follow-up and an event rate. Does that make sense? Okay. Yeah, it happens a lot. It happens where it looks like there should be a significant difference between curves, but maybe the number of events is just not high enough, or the length of follow-up wasn't long enough that you captured enough events, or you didn't have enough subjects. So there's a lot of things that go into survival analysis beyond just how many subjects do I have. There are other functions of survival time that are very interesting, and one of the most interesting functions is called the hazard. The hazard is a failure rate. So it really is representing how subjects are having events in your study period. In terms of statistics, it's essentially the probability of having the event, assuming the individual survived up until that point in time. So if we look at these different hazard functions, hazard really meaning, in English, risk, the risk of the event, sort of the instantaneous risk. So if I think about it, over time, do you really think that the risk of death in your study is the same from the beginning to the end? That's usually not the case, right? Usually the risk of death is either really high early on, and then if you survive for so long, then that risk kind of decreases, which would be this green function. So notice higher values on the y-axis correspond to higher risk of death at early time periods. So you can think about this in terms of breast cancer survivors, right? We know if you get them past that 5-year window, then their chances of relapse and then subsequent death are actually decreased, right? We've seen that. There's evidence behind that. So we think that in that case, there's a decreasing hazard function. So the rate at which the event occurs actually decreases over time. The further away you get beyond maybe remission in this case. There may be other disease processes where you know that the risk of death is increasing over time. So lots of people with a particular condition are going to survive, let's say, 10, 12, 15 months. But the further out they get, just by the process of the disease, or maybe the treatment stops working, stops being effective if it's like a cancer therapy, then the rate of the event occurring actually increases. So this is an increasing hazard. And then there are other cases, and I can't think of any off the top of my head, but if you have one, let me know. Actually, I can think of one. This bathtub shape, where you start off with this population, and the risk of death is relatively high early on. At some middle point, it decreases to a sort of a bottom. It bottoms out, but then it starts to increase again. So you can think of this as maybe a really severe disease where patients for which the treatment doesn't work will die early. So that's why we have an increased hazard here. Those patients have passed. The remaining patients are seeing benefit from treatment, so they're surviving longer. So the rate of death is going down, or the risk of death is going down. But at some point, that treatment stops working for them as well. And then you see the risk of death going back up. So the hazard functions are actually just as meaningful, if not more meaningful, about describing the event in your study. And they're ignored. Very often, when we're comparing groups, most people will assume that the hazard rate is stable, It's a straight line, meaning the risk of death at the beginning of the study is the same as it is in the middle, is the same as it is at the end. And if that's the case, then you could be making some serious errors in how you're trying to describe what's going on. Some more flexible methods will actually allow you to do group comparisons when you have different hazard rates. Has everyone heard of the Cox regression model? Cox regression is a very useful tool, but it's not, in its simplest form, useful when you have changing hazards or hazards in groups that are not what we call proportional. So you could have a decreasing hazard function in your group A, but you better have the same trend in group B, or that Cox proportional hazards regression model will not give you a valid result. So I'll briefly touch on that later. But I wanted to emphasize the hazard function because I think it's one that's overlooked in favor of the survival function very often. How do we interpret the hazard function? So it's the risk of an event occurrence at time t. Here's a good example. Let's suppose that in our study where our units of time is measured in months, and we compute a hazard for patients in this population contracting influenza over a period of time as 0.015. That's the value of the hazard over the time period, over the study time. What does that mean? Well, if you think about it in courses of months, it doesn't really make sense. The patient should expect to contract the flu 0.015 times over the course of a month, assuming a constant hazard. But if you multiply that out, it's 0.2 times a year, or approximately twice in 10 years, if the hazard stays constant. So that's how we could talk about hazard or risk of an event for something like contracting the flu. If there are no censored observations, which for us very rarely happens, the hazard function can be estimated as the proportion of patients that die in a small interval of time, given that they survived to the beginning of the interval. But again, very rarely do we have censoring, so there's some adjustments. How do we do stuff like this? The most common way to estimate that survival function here is through the Kaplan-Meier method. It's a non-parametric method. It's the most widely used. There are other ways of doing that. There's a way that actuaries use, but the actuarial method, which is called life table analysis, is really only appropriate when you have really, really large data sets. So large numbers of observations, many unique event times. So that's very rare for us whenever we're actually doing a study. How do we compare survival? So this kind of goes back to your question. Were you comparing using survival analysis methods, or were you comparing just the rate of events at 3 months? Uh-huh. I'm sorry, I couldn't hear you. Oh, so you didn't even have a survival analysis in that case. Oh, so yours wasn't survival analysis. So if you're doing serum biomarkers, were you looking at it as a continuous outcome? Then that would be a comparison of means. Is that what you're... Yeah, okay. So that really doesn't apply here. That would be the lecture from last Friday. But if you're interested in talking about that, you can always come up to the 5th floor and someone can give you a 1-hour consultation and talk to you about maybe how to power your study. Okay? If your question looks like, is the time to event different in Group A than in Group B, or the risk of something occurring at a particular point in time different in Group A than in Group B, then you have several options. The most commonly used, I think, at least whenever I look, is the log rank test. The log rank test is simple, very simple. The problem with the log rank test is if you don't have a constant difference between groups over time, it may not give you the result that you think is actually there. So, let me give you an example. Notice in this last scenario, what do we have? We have Group A and Group B. In Group B, the rate of events is pretty stable until about 40, and then it kind of slows down and tapers off. In Group A, the rate of events is a little bit less than that of Group B and pretty stable until you get to about 25, and then it flattens off. So when I talk about the difference is constant over time, I'm talking about the difference between these two lines, and that's diverging, right? The difference between the two groups in terms of survival is actually that long term or that late survival. There's really no difference. If we covered up everything from before about 30 weeks, there's no difference between those. But once you get beyond that, you see a long-term benefit. So a log rank test may not detect that unless this is a huge difference. So it may detect this one because it's pretty big. But if you see diverging curves, you want to use a test that weights long-term differences in survival more highly than short-term differences in survival. So log rank test, again, sort of assumes that the difference is constant over time, that it appears early and it's sustained. So it looks something like this. Notice that it appears early and it's sustained. Then we get some censoring out here. A Wilcoxon test will give higher weight or importance to earlier effects. So this is better when you have short-term differences in survival. So look at this middle example where it's converging. So you see an early benefit, and then it converges at the end. It comes back together. Sometimes this convergence actually occurs much earlier in the curves. And in that case, the Wilcoxon test would be more powerful for detecting that short-term difference because it would downweight the long-term survival. The Tyrone-Ware is a compromise between the two. There's actually a method called the Fleming-Harrington, which just allows you to specify where you want to weight importance. Early, late, middle, that kind of thing. So there are very flexible log rank tests that are not all that difficult to understand. But if you're just defaulting to the log rank test, you could be missing meaningful results because you could be underpowered. And the question is always, now again, this is the chicken and the egg thing. What do you do first? Do you look at the data and then pick the test? No, right? You probably anticipate short-term benefit, or you probably anticipate no short-term differences but long-term benefit. So if you specify that beforehand in your analysis plan, then you're transparent and you're doing something that really doesn't violate the scientific method. If you're just doing observational and hypothesis generating, then it may be okay to use a method based on what the data looks like, as long as you're trying not, as long as you say that this is a hypothesis generating experiment. Inferences on time to events. Let's do an example where we use a log rank test, and I'm going to show you how to break it down by another factor that may be prognostic for survival. So we have cancer here, and we're looking at two different therapies, an accelerated versus a standard therapy, or a control. This is head and neck cancer. Researchers are interested in exploring any differences in survival between the patients treated with the two different therapies. It's always important to look at Table 1. This is I should preface this by saying this is an observational study. They didn't randomly assign subjects to therapy. They were actually placed on therapy by their physician. They were just observing from patient records sort of what the survival was after the fact. So we have a gender distribution here, primarily males, a median age, and a range for age. the site of head and neck cancer, the stage 3 or 4, and then the tumor stage, broken down by distribution. So it's always important to look at this before you dive into analysis to make sure that, especially in observational studies, that there's no imbalance. And it turns out, of course, that there is some imbalance here that we'll look at in a moment. So the hypothesis for survival analysis for time to event looks like this. The null is that there's no difference in the two survival functions for accelerated and standard therapy over the entire time period of interest, versus there is a difference for at least one period of time from 0 to, it looks like, 120 months. And then what we have here are the Kaplan-Meier curves. The blue is accelerated, the red is standard, and then the black dots represent censored observations. So loss to follow-up, for instance, could be a reason. Or if it occurs at the end of this, it could be that that person, well, this is more an observational study, so it doesn't really apply here. And again, time in months across the x-axis. The probability of surviving up to time t is represented on the y-axis, or you can think of it as the percentage of patients still surviving at that time. So we have events pretty quickly. In fact, the two curves look like they follow the same path. They actually cross here, and then we see the standard therapy continues to decrease a little bit more rapidly. So the rate of events is occurring more rapidly in the standard therapy group relative to the accelerated group. But there's not a whole lot of separation. And then we see at about 18 months for both groups, well, actually in 18 months for the accelerated group, it starts to level off. So the rate of events kind of decrease there. Then it picks back up again, decreases. So we almost have two lines here for the blue group, right? We have one line that goes straight down pretty rapidly until about 18 months, and then another line that flattens off. The slope is not quite so negative for the remaining period. So you can think of the slopes of those lines as describing what's happening to these subjects in terms of the event. Rapid decrease, so rapid event rate early on to 18 months, and then it flattens out. So the event rate decreases from 18 months out to 120 months. For the standard therapy, I would argue that you have a straight line down until about 24 months, and then everyone else is censored after that. So we really don't know what happens out here because we didn't observe any more events. Do you think that this is statistically significant? Does it visually appear significant? Yeah, it doesn't to me either. Turns out that if I do a log rank test, the p-value is 0.5. The median survival times for the two groups is a difference of only 5 months. We had 2 censored in the accelerated and 5 censored in the standard. So you can see the 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. That must be the 5th, and then that one in the blue. So we could stop there, or we could go back and observe that this is an observational study. We have to make sure that there's not something else that could be masking any effects of treatment. It turns out that the accelerated group has 86% stage 4. The standard group only had 50%. Why would that be? If these subjects are not being randomized, it could be that physicians are placing their more advanced stage cancers into an accelerated therapy that may have more risks, but it may work for them. And then being more conservative with those who don't have quite the advanced stage of cancer. So it would make sense that anything that's prognostic for patient survival, in particular if it's imbalanced between groups, we should try to consider it when we're doing an analysis. The easiest way to do that is to create stratification here. So basically we now have 4 groups. We have broken down our advanced and our standard therapy into stage 3 and stage 4. What do we notice right off the bat? Now I don't have, okay, stage 4 for the advanced is 25 subjects. Stage 3 for the advanced is 4 subjects, and then 8 and 8. So we have some small sample sizes here, but that's okay. The red line, stage 3, again, that's only 4 subjects. But if you'll notice, we had one subject who had an event at 24 months. We had one subject that had an event at 36 months. One subject was censored at about 96 months. And the last subject had an event at somewhere between 108 and 120 months. For the other 3 groups, what do we notice? They're kind of clustered, right? So even though we have small sample sizes, even with only 4 subjects in that stage 3 group, we're seeing marginally significant differences when we do a log rank test. So 0.07 is marginal significance, and I would argue that the reason it's marginal is because we're doing this on a very, very small sample size. If we could increase our number of observations, that may be even more apparent and make that p-value less than 0.05. In fact, if it's broken down by stage, the median survival times are pretty compelling. Stage 4, so the more advanced diseased patients who got standard therapy only survived, on average, 8.8 months. Those that were stage 3 on the standard therapy, 2 times that, about 19 months, but still not very good survival. Accelerated therapy, stage 4, 16 months. Actually not as good as the standard for stage 3, so there's a disease effect there, right? But if they had a stage 3 and were given accelerated therapy, almost 80 months. And that has probably a little bit of bias because there's 4 observations, but yes. It means that there's censoring. So that, yeah, I think I've had this question before for this graphic. Why does this one drop all the way to 0 when they're censoring? And it shouldn't. This one indicates that approximately 25% were censored. Approximately 10 to 15% of these were censored. It turns out for this one, and I don't know which group it falls in because there are 2 that were censored in the accelerated group. Let's see. Accelerated is red and green. It looks like one was in the stage 3 and one was in stage 4. This should technically only drop down to 0.25. But the curve, it looks like this was generated, I don't know what software this is actually. It doesn't look like one that I've used before, but it looks like it should stop at 0.25. Yeah, the green for stage 4, there were 25, and 1 was censored, so I mean it probably should stop here. I'm guessing that's this should not drop all the way to 0. It's misleading, and this should not drop all the way to 0. This should drop down to 0.25 because at the end of the study, 75% of the subjects had an event. 1 was censored. Here, 1 was censored, so 1 out of 25, whatever that percentage is where it should drop down to. The remaining had events. And it looks like these curves are accurate because out of the stage 3, we had 5 censored. 1, 2, 3. It looks like about 3 in this blue, and it doesn't drop all the way down to 0. It drops down to about 30%. And this one doesn't drop all the way down either. It looks like it has two events in this one. So 2 out of, how many, stage 4? 2 out of 8. So that's about right. Okay? Yeah, this is an old picture. I don't have the actual data, so I don't have a way to fix that graph. I guess I could just kind of put a little thing over it, but I'm not going to do that. So yeah, p-value 0.07. Again, a pretty significant result for such a small sample size. And a very, very big difference in terms of median survival. So time to event, again, The response is interesting because it has more information than just a yes-no outcome. It also attaches to that yes-no a continuous timing of that event. There are non-parametric methods like the log rank test or the Fleming-Harrington method that we talked about that can be used. Your choice among those should be based on whether you anticipate short-term, long-term, or overall benefit for your analysis. The log rank test, which is what most people default to, is really only optimal when the survival curves are approximately parallel the entire study period. So you should think about weight functions based on your clinical knowledge and try to pre-specify them if this is an experiment that needs to be more confirmatory rather than hypothesis generating. And then, of course, we've talked about the fact that survival analysis does not only apply to events like death or even events related to health. This is a really fun example that I found online in terms of publication bias. And it actually relates back to what we talked about in one of the first two lectures, which was publication bias. When you're searching literature, unfortunately, you're not getting a complete picture of what's really going on because there's delayed publication for studies that don't have significant results, meaning it takes longer to get them published. Either it takes longer for the authors to get it out or longer for the journal to accept it, or both. In addition to that delay, there's also fewer of them overall being published. So if you don't get a significant result, you don't publish it at all. Or you try to publish it, but the journal won't take it, and then you table it for something else. So what do we see here? We see Kaplan-Meier curves for 3 different types of studies. The x-axis is the number of years. The y-axis you can think of as the proportion not published. So when it drops, you have a publication. When it drops, again, a publication. The more rapidly it's dropping, the more rapidly they're getting published. What drops the quickest? Studies with significant results. When I say significant, I mean usually p-value of less than 0.05. And it's pretty constant. What are the other two? A non-significant trend is this darker gray. It's actually this top line. Non-significant trend, that's usually what we call marginally significant. And then a null study means that there's no significant results. P is much greater than 0.05. So the rate and the timing of publication is definitely influenced by the type of result. And it's not just on the author, it's on the journals as well. So the title of this was Publication Bias, Evidence of Delayed Publication in a Cohort Study of Clinical Research Projects. Here is a nice table from the manuscript. Risk factors for time to publication using univariate Cox regression. So using survival methods to look at not only whether or not something's being published, but the timing at which it's published. And they have the 3 different groups. The interpretation, studies with significant results, meaning a p-value less than 0.05, have a 2-fold higher incidence of publication compared to studies without a significant result. And that's from this hazard ratio. The hazard ratio, which we didn't talk about in the previous slides, is essentially comparing the hazard rate for one group to some control hazard. And in this case, the control hazard rate is the null. If you see, it's almost like an odds ratio. If you see a value greater than 1, you know you have an increased incidence of events, or increased risk of the event. And the event in this case is publication. So significant results are over 2 times as likely to be published over the study period as a paper with a non-significant result. Any questions about survival analysis? I will briefly talk about Cox regression at the end of the talk. No questions? Let's get into correlation and regression. So linear correlation is probably, most of you probably fundamentally understand it. You essentially have two continuous variables, and you think that a line would describe their relationship. The primary difference between doing a correlation between x and y and doing a regression between x and y is what you really want to say about x and y. So if you're interested in describing the relationship functionally, like for every unit change in x, a unit change in y is observed, then you would want to do regression. But if you're just interested in the strength of the association, meaning what percentage of the variation in y can be explained by x, or is it a positive or negative relationship, those things really can come from linear correlation. So again, when would you do regression? When you want to functionally describe, when you want to describe the functional relationship between two continuous variables. Here's an example, again, an old example that's been used, I think, even when Dr. Mayo taught this course when it first started. Along the x-axis, we have alcohol consumption in liters per person per year. Along the y-axis, we have the death rate due to cirrhosis per 100,000 people. And the scatter plot here represents several different countries, and they're labeled. This is old. How do we know it's old? Because there's West Germany here. Oh, also it says 1979. So this is an old, but it's a fun example to use whenever you're talking about correlation. To interpret a scatter plot is usually the best way to visualize the relationship between two continuous outcomes. We see a cluster, and it's an increasing relationship, right? And a line would reasonably describe that relationship. So as alcohol consumption increases, the rate of death due to cirrhosis is increasing as well. Another funny factor of this data is look at France way out here. They're so, at least among the countries that they looked at, France is much higher in terms of their alcohol consumption and their death rate. The rest of them are kind of clustered here. USA's lodged right nice in the middle. So if we want to know the strength of association between these two variables, we would want to use something like Pearson's correlation coefficient. Notice it's a function of whatever your x variable is, in this case the alcohol consumption for a country, and then it's a function of the y as well, which is the death rate due to cirrhosis. And it's looking at deviations from the overall mean alcohol consumption and the overall mean death rate of the data points in your sample, and it's standardizing it by something down here, and it's taking a sum for all of the different observations. R does have some restrictions. If you have a really small sample size, you probably shouldn't use it. If you have non-normal data, you shouldn't use it. If you have data that looks like it's not a linear relationship, which tends to occur when you have non-normal data, then you shouldn't use it. If you have non-normal data or small sample sizes, there is an alternative called Spearman's coefficient, which goes off the rank rather than the raw data values. And here are some values of R and their corresponding scatter plots. So R is just like a slope. R will be less than 0. It'll be negative if you have a negative slope. If you put a line through there, the slope would be negative. R would be greater than 0 if you have a positive relationship, meaning as x increases, y is increasing. And then when you have really no relationship at all, you tend to see data that just looks like noise. Maybe it's a circle. There's no apparent relationship, meaning for small values of x, I have small and large values of y. I have small and large values of y really across the whole range of x. So in that case, R would indicate that there's no strength of relationship by giving you a value very close to 0. When we do inferences on correlation, sometimes we actually want to do a hypothesis test to see whether or not things are significantly correlated rather than just giving a correlation coefficient. You can actually do a hypothesis test where your null hypothesis is that there's no linear association between X and Y. So in this example, there's no linear association between cirrhosis and death rates, and alcohol consumption. You're hypothesizing that the population correlation, rho, is equal to 0 versus some other kind of relationship, either a strong increasing or strong positive linear relationship by using that greater than 0, a strong negative linear relationship, which would be less than 0, or maybe you don't know if it's positive or negative, or you really don't want to pre-specify, so you just say, if it's positive or negative, I want to detect it. So you do, it's just a strong linear relationship, meaning the correlation coefficient is not 0, it's either negative or positive. And it turns out for this kind of test, we use a t test statistic, just like we did last week. Its calculation is different. Its degrees of freedom are 2, but it is a t. This is some SAS output using the correlation procedure. 2 variables, alcohol and cirrhosis. There are 13 observations, and notice it specifies here. We're testing the null hypothesis that rho is equal to 0. And this is very typical output when you're doing correlation. It's essentially a matrix of values where the row and the column have the 2 variables of interest, and within the cells of the matrix you have the statistics. So the top value is the correlation coefficient R, and the bottom value is the p-value. So what this says is that the consumption of alcohol is very, very highly associated with cirrhosis death rates. R of 0.95, a p-value of less than 0.001. How do I know that this is very large? What's the biggest value R can take on? 1, right? 1 means a perfect positive linear relationship. -1 means a perfect negative linear relationship. So this is almost a perfect positive linear relationship. There's a problem with this number, though. It turns out when you have a guy here like France who's out there all by himself, he can artificially inflate your correlation coefficient. So you have to be very careful when you have outliers. Let me draw you a line. So this is probably what a line would look like to describe that relationship. France is an outlier, but thankfully for us, if we were to draw a line excluding France just through these data points, it would probably still go through France. But he's still making it look like there's a lot of correlation simply because he's so far out there. We could get into that, but we don't really have time. What would be even more problematic would be if France were here. What would that line look like? He would have low alcohol consumption and very high death rates due to cirrhosis. So if we try to describe the data, the relationship without France, let's ignore France here, then we would still have a line like this. But if we included this type of outlier, the line would look like that. Because we have a cluster of points and what's called an influential observation. It would actually change the relationship. In that case, you would not want to use Pearson's correlation coefficient or linear regression. You would need to think about even including this, or whether some other more sophisticated method would have to be used to describe the relationship. You may also want to observe France and think about, well, why would they be so different in terms of their death rate due to cirrhosis? It could be that there's something else going on with France that would cause you to exclude them from this analysis. So without France, if we excluded them, notice that the correlation coefficient is still very high, but it does drop a little bit. So So you had artificially inflated it having France way out there. Related to correlation is regression, in particular linear regression, which is probably what you all are most familiar with. Regression methods are very useful when you want to incorporate other factors into a test of a treatment effect, or you want to adjust for other explanatory variables when you're looking at the association between things. The different types of regression methods that can be used. Again, you guys are probably most familiar with linear regression. Linear regression assumes that your dependent variable y is continuous and approximately normal and related to your independent variable x linearly, meaning a line could describe the relationship. That's simple linear regression. Another type of regression that's common is what's called logistic regression. Logistic regression really is the same thing as linear regression. You're trying to describe an outcome using an independent variable x, but your outcome now, your y, is not continuous. It's a category, and that category actually, it's a categorical outcome, and it only has two different categories. So yes or no, success or failure, male or female, disease or no disease. That's when logistic regression is useful. There are other types of logistic regression. This is, if you wanted to be specific, it's called binary logistic, or binary logistic regression. You could have multinomial logistic regression when your categorical outcome has more than two categories. So it could be three different classes, X, Y, Z, and you're interested in predicting or estimating which student would go into which class based on some characteristics of the student. Ordinal logistic regression takes that a step further when your outcome is categorical but also ordinal. So if there's ordering. So a good example of that would be tumor response, where you have a categorical response, but it also has some inherent ordering. Complete versus partial versus stable disease versus failure would be a useful way of thinking of ordinal logistic regression. Analysis of variance, ANOVA, is actually regression. It's just a specific type of regression when you have categorical X's. And really nice things happen when you have categorical X's. So those are 2- and 3-way ANOVA. And then, of course, when you have a time-to-event outcome, you can use Cox regression models to adjust or control for other factors. Let's get into linear regression first, because I think it's the simplest. When you're trying to describe the relationship between two continuous variables, x and y, you would use something like simple linear regression. So again, in correlation, you have an x and a y, but one of them is not fundamentally the independent and the other the dependent. And you're really not interested in their functional relationship, just the strength of their association. When you have a true independent and dependent variable, or you are interested in how functionally they're related, you would want to use something like this because it allows you to describe how changing x results in changes in y. So some examples, supplement dose during pregnancy and birth weight of babies. Note here, though, that dependent does not necessarily mean x causes y. It just means that we assume y is dependent upon x. So in its most simple form, we have what looks like the equation of a line with a slope, beta 1, and an intercept, beta 0. And then we have that random error, that probabilistic component that has to account for unexplained variation in the relationship between x and y. When you have a single x in your model, you have what's called simple linear regression. And again, most of our inferences are going to be around this piece right here. How does changing x affect y? So if I had a perfect linear relationship, then I have data that follows an exact line. This example, we have an intercept of 0 and a slope of 1. So this is beta 1. How do I interpret that? Just like you interpret the slope of a line back whenever you first learned about it in elementary school. For every unit change in x, I see a unit change in y. Now, we don't get data that looks like this. We get data that looks like this, where a line can approximate the relationship, but we have scatter or errors around the line. So the pieces of the line that describe, let me erase this. What are they actually describing? Well, the intercept describes where the line would cross the y-axis at x equals 0. So 0.78. The slope, again, for every unit change in x, I see 0.89 unit changes in y, whatever the units are. And then epsilon describes this distance, the vertical distance between the actual observation and the line that describes the relationship. So, of course, we want those epsilons to be small, which means we have a really good line. The statistical method that fits the line, that finds the estimates of beta 0 and beta 1, is actually the line with the slope and intercept that minimizes those distances. Here we have an example where we have anthropomorphic measures on 150 children, and we want to know the relationship between two variables, average arm circumference and height. So I've given you some summary statistics in terms of the average arm circumference, the average height, the range for these 150 children. Linear regression in this case is a potential option because it allows us to describe the relationship between these anthropomorphic measures, which may be of interest to us. The line that we're going to get from this, its interpretation is the mean value of y for every value of x in the sample, and we can also use the slope to talk about differences between children's height for different values of their circumference, arm circumference. So here's a scatter plot. X-axis is height, y-axis is circumference, and we can see that a line could reasonably describe that relationship. If I saw something that looked like this, I would not want to use linear regression. There are regression methods, but it would be you would have to include like a squared term in there to kind of describe it, and it would be less, I think, meaningful, be at least more difficult to interpret. The line that we estimate will be of this form. So y in this case is going to be arm circumference, x will be height. And the line fit to this data using statistical software is, this is the estimated intercept, 2.7, and the estimated slope, 0.16. What do these things mean? Well, we can use the values of y to talk about what children with certain heights would have in terms of their arm circumference. So if I plug in 60, it tells me what the average or expected arm circumference would be for children whose height is 60 centimeters. And that is 12.3 centimeters circumference. We can also interpret the slope. So the slope here was 0.16. We need to know the units, centimeters and centimeters. Units are important. So how do we interpret that? The average change in arm circumference for a 1 unit increase in height. Unit in this case is centimeters. So for every 1 centimeter increase in height, we see a 0.16 centimeter increase in arm circumference. We can also look at the mean difference in arm circumference for two different groups of children who differ by so many units. So for instance, if they differ by only 1 centimeter in height, then they should differ by 0.16 centimeters in arm circumference on average. What if we were interested in more than just 1 unit? Say we were interested in 10 units. So 1 centimeter would be equivalent to 0.16 change. 10 centimeters is just 10 times that. So if they were 60 centimeters versus 50 centimeters tall, 10 times 0.16 would give me the expected difference in their arm circumference, 1.6 centimeters. And that's this distance, 1.6 centimeters. Notice I keep using the word expected. Expected in statistics is just another word for average, the average difference in arm circumference. One huge thing to take note of for regression is you never want to extrapolate, ever. If you did not see beyond here, you really don't know what happens out here. So I cannot take this analysis and say, for children whose height is 90 centimeters, I cannot extrapolate this line out there and say anything about their arm circumference. Because very often what could happen is you'll reach a point at which the relationship changes or no longer exists. This data could plateau off at some point. And then you would have a big difference between what was actually true and what you would have predicted from the extrapolation. So limit your interpretation to actual observed ranges of X. If you need to interpret or you need information out here, then you need to go and sample out in that area of the x-axis. So we've talked about the slope, which is usually the most important parameter in a regression model, but what about the intercept? Sometimes the intercept actually is meaningful. The intercept's interpretation is just the estimated or expected value of your response y when your x is equal to 0. So if x, whatever x in your model is, if it has meaning at 0, then the value of y at that point may have meaning as well. But in this example, 0 on the x-axis indicates children who are 0 centimeters tall. So it really doesn't have any meaning. So in this case, the intercept is just needed to specify the line. It's really not on its own meaningful. In fact, if you look, the lower end of our x-axis is at 40. So we would have to extrapolate to even interpret that, and we don't do that. How do we do inferences? We do inferences in linear regression the same way we did them in correlation. We make inferences on the slope. So if the slope is 0, there's no relationship. If the slope is positive, there's a positive linear relationship. If it's negative, there's a negative linear relationship. Or we could be just interested in showing there's a relationship. In that case, we wouldn't specify positive or negative. The test statistic is a t. Notice that it looks an awful lot like the correlation coefficient from before. And that's because the correlation coefficient r and the slope beta 1 are directly related to one another. If we wanted to extend, and very often this is the purpose of regression, if we wanted to extend this beyond 1x, then we would do something called multiple linear regression. Notice now I have what looks like an intercept and a bunch of slopes. And really that's what they are. They're slopes, but they're not in 2 dimensions. They're in multiple dimensions. Sometimes we only have one x of interest and we're adjusting for other things. So here's an example of how we would interpret an analysis from a multiple regression. Suppose we have a linear regression model where we're interested in predicting or estimating birth weight, which is our y, from dose of a supplement during pregnancy, which is our X. But we know that this relationship could be affected by two other things: gestational age of the baby at birth and gender of the baby. Because those two things could affect birth weight, correct? So we would do a multiple linear regression model where really we're only interested in this, X1, which is dose, and beta 1, which describes the relationship between dose of the supplement and changes in birth weight. How do we interpret the parameter beta 1, though, in this context when we have other X's in the model? The way that you would interpret it is to say that among babies of the same gender and gestational age, or similar gestational age, for every 1 unit change in dose, birth weight changes by beta 1 units. So whatever beta 1 is. If it's 0.4, it's 0.4 units. And it's important that we understand that what we're essentially doing is holding the other variables constant. So I really can only interpret beta 1 if all my babies are male, all my babies are female. I'm holding those other variables fixed. It's not just the raw relationship between birth weight and the dose of the drug. Now briefly, I'm going to touch on logistic regression and Cox regression, and this is where we'll stop. I won't have time for those additional slides, but I will send them to you if you're interested. Logistic regression is just like linear regression, only now instead of y being continuous, y is what we call dichotomous, categorical. It's nominal. It's a yes-no outcome. And what we're trying to predict looks a lot like the right-hand side is the same, the left-hand side is totally different. Just know that this is the log odds of an outcome, where the pi that you see here is the probability of, let's say that this is response, that they respond to treatment. Pi is the probability that they respond to treatment, given their value of x. And we're describing it using a line relating to the log odds. But I think it's easier to see on the raw scale. So this is an example where x is temperature and y is the response. Remember, y is a yes or no. So it's either a 0. Notice these. This is a scatter plot. These are all zeros. These are all ones. What do you see here? I see that for temperatures that are lower, 30 or less, you tend to get zeros for your response. For temperatures that are 30 or greater, you tend to get ones for your response. And there's a certain area here, right, where you get zeros and ones. And that's where the line changes. And this line is describing the probability that y is equal to 1. So notice the probability that y is equal to 1, where we have all zeros, is very small. The probability that y is equal to 1, where we have all ones, is basically 1. And then in between those two places, we shift. We increase in probability until we get up here to this range where we get primarily ones. This is called a logistic function. For those of you who do basic science, you see sigmoidal curves all the time. This is just a logistic model. But we don't talk about things in that way. We typically estimate it using the log odds, so we can use a line. But again, this is y, and the probability that y is equal to 1 can be described using a logistic model just like this. The interpretation of the coefficients is not straightforward in logistic regression because they're describing the relationship between x and the log odds of y being response rather than between x and just y. In logistic regression, we also very often report odds ratios to describe treatment effects or differences. Here's an example of interpretation of coefficients from a logistic regression model. Suppose our outcome is death subjects are either classified as dead or alive. And then our factor of interest, X, is a treatment, either intervention or standard of care. This is our logistic model. We have a linear function here, a slope and an intercept, and we have log odds, where pi is the probability that a subject will die given whether they got the intervention or standard of care. X1 will be intervention, X2 will be standard of care in this equation. Suppose we run this analysis, and in this model we get beta 1, that slope, estimated as negative 0.69. So how do we interpret that? It is, in a way that's hard to think about, for every 1 unit change in X, or going from intervention to standard of care, it is the unit change in the log odds of Y. And that makes no sense whatsoever, right? But if you exponentiate it, if I take EXP of beta 1, then it does have meaning. You get the odds ratio relating treatment to the probability of death. So exponentiate that and I get 0.5. When treatment involves the intervention, the odds of dying decrease by 50% relative to standard of care. How do I know they decrease by 50%? Because if they were equal, it would be 1. Anything less than 1 would be a decrease. Anything greater than 1 would be an increase. So 0.5 is a 50% reduction from 1. You can also notice the negative sign on the raw value of beta 1. That indicates a decrease in the chances of death, but it's difficult to interpret without transforming it. Suppose we have beta 1 estimated to be 0.41. What does that mean? Exponentiate it, and you get a 1.5. When treatment involves the intervention, the odds of dying increase by 50%. Notice it's 0.5. It's 50% more than 1. That's relative to standard of care. And that's also indicative because of the positive sign in front of the beta. So you get an increase in the chances of death. When X is continuous, so previously we had X being treatment or control. What if X is age and Y is still death? So X is a continuous value. And we get a slope parameter of 0.095. Exponentiated again, but the interpretation is a little bit different. It's actually similar to the linear regression example we had before. For every 1 year increase in age, the odds of dying increase by 10% because we have 1.1 when we exponentiate it. Again, positive sign tells us there's an decrease in the chances of death, but it's difficult to interpret without a transformation. If you did multiple logistic regression, meaning if you go back to this formula and you had a beta 2 and an x2, other variables that you were interested in, the interpretation of the regression coefficients is the same. You can still exponentiate and get meaningful results, meaningful interpretation for those in terms of the odds. But you would have to take them in terms of partial regression coefficients, just like when we had the multiple linear regression example for the dose of a supplement and birth weight of babies. You have to be careful that you say, I'm holding everything else fixed, and this is the relationship between X and Y. Briefly, Cox regression and logistic regression, I wanted to talk about how Cox regression is really very similar to what logistic regression is doing. Cox regression is describing a yes-no outcome, but it's incorporating the timing of the outcome into the modeling. And the distinction is that one would result in something like an odds ratio, that's logistic regression. The other results in something called a hazard ratio. So the hazard ratio is a ratio of incidence rates. Incidence rates are those hazard functions, the number of events per population at risk in a small unit of time. Odds ratio is a ratio of proportions. Proportions is really a cumulative number of events over the entire study period. By taking into account the timing of the events, you're actually collecting more information than just a binary yes-no. So Cox regression could be more powerful at finding differences than just the yes-no. The biggest problem with Cox regression is that its entire title is Cox proportional hazards regression. So you have to check the proportional hazards assumption, and we talked about this already. Proportional hazards means that the difference is maintained and not converging or diverging, because what you have here is hazard function that's changing over time, and it's not changing the same way in both treatment groups. So you're violating an assumption of the Cox model. Cox regression is what we call semi-parametric, so it does have some parametric assumptions. Kaplan-Meier is a non-parametric method, but there are fully parametric survival methods that assume that the survival times are following some kind of probability distribution, like an exponential model. That is beyond the scope of anything that you guys would ever do on your own. But if you're interested in learning more about these methods, there is a class devoted specifically to survival analysis, which would have you do some of this, but it is a full semester course. The nice thing about Cox regression, though, is if you've not violated the assumption of proportional hazards, you can do the same types of regression analyses we just did for logistic and linear regression. And you can also incorporate things that are changing over time, which are called time-dependent covariates. So an example of time-dependent covariates would be if you're evaluating the effect of taking oral contraceptives on stress fracture risk in women athletes over 2 years, their exposure to oral contraceptives changes over time. They may switch on or off of them over the 2-year period. So that's important to know in the modeling procedure. If you just examined the risk of stress fracture by their use at baseline, you may not see anything because there's a lot of noise in your exposure variable. But if you incorporate the times of starting and stopping oral contraceptive, you may actually see something arise. No time permitting, but there is, if you're interested in incidence and prevalence slides where I talk about incidence rates, prevalence rates, diagnostic testing, and sensitivity and specificity, positive, predictive, negative predictive value, I can send you these slides. Otherwise, please go and evaluate the course from our website. Jackie Jorlin will be sending you an email. Just click on the link and go and give us some good feedback. That way we know what to cover next year. For instance, if you want more survival analysis, or if you would like to see Poisson regression, or some other specific technique that you've been looking at, let me know, and I'll try to incorporate it for next year. The earlier I know, the better. Thank you all.